Every machine you use that acts intelligent. Your thermostat holding temperature, your phone navigating with GPS, your car's cruise control, every drone in the sky, every SpaceX rocket landing itself on a boat at sea, every pacemaker keeping a heart in rhythm, the autopilot on your flight last week. All of it secretly runs on one branch of mathematics. It's called control theory. It's what lets machines behave reliably in a messy, uncertain, unpredictable world full of wind, gravity, noise, and surprise. It's the reason anything engineered actually works. Over the next 15 minutes, I'm going to walk you through the entire toolkit, from the simplest feedback loop all the way to model predictive control and Kalman filters. Bottom up, every concept explained. By the end, you'll see feedback loops everywhere. Let's go. Let's start at the very beginning. You have a system. Engineers call it the plant. You want it to do something specific. Heat a room to 70 degrees, spin a motor at a target speed, land a rocket on a specific spot. So you apply some input and you hope for the best. That's called open-loop control. A microwave timer is the classic example. You set 30 seconds, it runs 30 seconds. It doesn't matter if your food is frozen solid or already room temperature. The microwave doesn't know, doesn't care, and doesn't adjust. Same story with a toaster on a timer or a sprinkler on a schedule. Open loop is simple, cheap, and works just fine as long as the system is perfectly predictable and nothing ever disturbs it. But the real world? The real world has gusts of wind, friction that changes with temperature, parts that age, sensors that drift, people pushing on things. In the real world, open loop fails almost immediately. You need something smarter. That something smarter is feedback. It's the single most important idea in all of engineering, and it works like this. You measure what your system is actually doing. You compare that measurement to what you want it to do. The difference, the error, gets fed into a controller that decides the next move. Then the system responds, you measure again, compare again, act again. Round and round. Measure, compare, act, repeat. Thousands of times a second. That tiny loop is everywhere. It's in your thermostat kicking on the heater when a room gets cold and shutting it off when it's warm enough. It's in your car's cruise control, adding gas on a hill and easing off on a decline. It's in every drone hovering, every rocket landing, every autopilot flying. Once you see the feedback loop pattern, you see it in literally every engineered system on Earth. It's the atomic unit of machines that behave intelligently. Now, to analyze any of this mathematically, engineers use transfer functions. Here's how it works. Take your system's differential equation, the physics of how it evolves over time. Apply something called the Laplace transform. This flips your equation from the time domain into the frequency domain, turning tricky derivatives into simple algebraic multiplications. Then you divide output over input. What's left is a compact little expression. We call it G of S. That fully captures how the system will respond to any input you can throw at it. A step, a ramp, a sine wave? G of S tells you. And the beauty is, once you have G of S, the entire toolbox of control theory unlocks. You can analyze stability. You can predict response. You can design controllers mathematically, all from one equation. The simplest dynamic system you'll ever analyze is called first order. Think heating a room, an RC circuit charging up, a cup of hot coffee cooling toward room temperature, population growth with decay. First-order systems are defined by a single parameter, the time constant, usually written as Greek letter tau. Kick the input up with a step, suddenly turn the heater on, suddenly connect the battery, and the output rises smoothly and exponentially toward the new target. After 1 tau worth of time, you're 63% of the way there. After 2 tau, 86%. After 3 tau, 95. By 5 tau, you're essentially done. No suggestion, no verso. Just a clean, exponential approach. First order is the base case of all dynamic analysis. Understand it, and everything else builds from here. Now add inertia to your system, and you get second-order dynamics. A mass on a spring with a damper. A pendulum swinging. En RLC circuit. Your car suspension when you hit a pothole. Suddenly 2 parameters matter instead of 1. The first is the natural frequency, omega n, which is how fast the system wants to oscillate if left alone. The second is the damping ratio, zeta, which is how much resistance there is to that oscillation. Zeta is where the magic happens. If zeta is less than 1, the system is underdamped. It rings, it overshoots, it bounces back and forth around the target before finally settling. If zeta is exactly 1, you get critical damping, the absolute fastest possible settle to target with no overshoot whatsoever. And if zeta is greater than 1, the system is overdamped, slow, steady, sluggish, no oscillation. Pick your poison. And here's the thing. Almost every mechanical and electrical system you'll ever encounter falls into one of these 3 regimes. Suspension systems, audio speakers, cranes, camera gimbals, all of them second order. Here's where it gets properly beautiful. A transfer function has poles, the values of S, where the function blows up to infinity. Plot those poles on the complex plane, with the real part on the horizontal axis and the imaginary part on the vertical axis, and you can see the entire personality of your system at a single glance. If every pole sits in the left half of the plane, the system is stable. Any disturbance, any initial condition, any weird kick, it all decays smoothly back to 0. If even just one pole creeps into the right half plane, the system is unstable. Any tiny perturbation causes the response to explode exponentially. If poles sit exactly on the imaginary axis, you get perpetual oscillation that neither grows nor decays. And the geometry tells you even more. The distance of the poles from the origin, that sets the speed of response. The angle of the poles from the real axis, that determines the damping. Pole position is literally the DNA of your system. Move the poles, and you change everything about how the system behaves. This is why half of control theory is about deliberately placing poles where you want them. Okay, now let's change our perspective entirely. Instead of step inputs, drive the system with a pure sine wave. Something beautiful happens. The output is another sine wave at exactly the same frequency, but scaled by some amount and shifted in phase. Now sweep the input frequency from very slow to very fast, recording how the output amplitude and phase shift at each frequency you try. What you get back is a Bode plot. 2 graphs stacked on top of each other. Magnitude on top, phase on the bottom, both plotted against frequency on a logarithmic scale. This is the system's frequency fingerprint. It tells you at a glance. Where does this system amplify signals? Where does it kill them? How much lag does it introduce at each frequency? Bode plots are engineering superpowers. From one picture you can read off bandwidth, resonance peaks, cutoff frequencies, roll-off rates. Every filter you design, every control loop you tune, you'll look at its Bode plot first. Harry Nyquist, working at Bell Labs in the 1930s, came up with one of the most beautiful ideas in all of engineering. Take your open-loop transfer function, controller times plant. Trace the path of that function as S travels around a specific closed contour in the complex plane. The curve you get back is called a Nyquist plot. Now look at the point -1 on the real axis. Count how many times your Nyquist curve wraps around that single point, clockwise versus counterclockwise. That count, combined with the number of unstable open-loop poles you already have, tells you exactly how many unstable closed-loop poles your feedback system will end up with. It's a complete stability test. No solving diferencial equations. No computing roots of polynomials. Just counting how many times a curve loops around a point. Elegant doesn't even begin to describe it. And the same plot also hands you gain margin and phase margin, exactly how much extra gain or extra phase lag your system can tolerate before becoming unstable. This is control theory at its most geometric and its most beautiful. Most of the real-world controllers operating right now, in industry, in cars, in drones, in chemical plants, in your home, are PID. 3 letters, 3 knobs. P stands for proportional. The output is proportional to the current error. Far from the target, push hard. Near the target, push softly. I stands for integral. Sum up all the past error over time, which is great for eliminating persistent bias like a steady headwind or a loaded spring. D stands for derivative. Look at how fast the error is shrinking and hit the brakes if you're rushing toward target too quickly, preventing overshoot. Tune those 3 gains intelligently, and you can stabilize almost any system you'll ever meet. 95% of all industrial controllers on the planet are PID. Not because it's the best, sometimes it isn't, but because it's simple, robust, easy to tune, and good enough for 95% of problems. It's the Swiss Army knife of control theory. Classical control, the transfer function stuff we've been discussing, handles systems with one input and one output. But what if your system has multiple inputs, multiple outputs, and dozens of internal variables? That's where modern control comes in, built on state space representation. You represent your system with a vector of state variables. Each one is some physical quantity: position, velocity, angle, temperature, current, voltage. Then you write the dynamics as a matrix differential equation. X dot equals a times x plus b times u. Y equals c times x plus d times u. Just matrices and vectors. Now suddenly you can handle aircraft with 6 degrees of freedom, robot arms with 20 joints, chemical plants with 100 variables, spacecraft attitude control in 3 dimensions. Linear algebra becomes your whole toolkit. This is where control theory grew up from clever engineering tricks into a serious mathematical discipline. And modern tools, LQR, Kalman filters, MPC, all live in this state space world. If your system is linear and you want the provably best possible controller, there's an exact answer: LQR, linear quadratic regulator. You write down a cost function, put numbers on how much you dislike position error, how much you dislike velocity error, how much you dislike using control effort. Plug it all in. LQR solves a matrix equation called the Riccati equation and hands you back a gain matrix K. That gain, applied as feedback, is mathematically proven to minimize your total cost over infinite time. It's optimal, not approximately, provably. But here's the catch. LQR needs to know the full state of your system, and real sensors don't measure everything. And what they do measure, they measure with noise. That's where the Kalman filter comes in. The Kalman filter takes your noisy, incomplete measurements, combines them with your system model, and produces the best possible estimate of the true hidden state, optimally weighting prediction against measurement. The filter estimates, the controller acts on that estimate. Together, this combination is called LQG, linear quadratic Gaussian. The Apollo moon landing ran on LQG. Every commercial autopilot since, every modern spacecraft, every Tesla on autopilot, every drone that hovers perfectly still. Model predictive control takes everything we've discussed and pushes it further, way further. At every single control tick, typically 10 to 100 times per second, the MPC controller does something wild. It simulates the system forward several seconds into the future. It asks the question, given my current state, what is the best sequence of control actions I could apply over the next, say, 20 time steps into the future? Then it solves a massive optimization problem to find that optimal sequence. Applies only the very first control action, throws everything else away, and then at the next tick, it does the whole thing over again. MPC is computationally expensive, but it handles things that LQR can't. Hard constraints. Don't exceed maximum thrust. Stay within the lane markings. Don't hit the pedestrian. Respect battery current limits. Don't let the chemical temperature go over 500 degrees. It can even handle nonlinear dynamics with local linearization tricks. Tesla Autopilot runs on MPC. Every modern industrial refinery, every factory robot arm, power grid frequency regulation. It's the state of the art. So where does all this math end up in the real world? Control theory is quite literally everywhere. SpaceX uses it to land rockets on floating barges in the ocean. Drones use it to hover perfectly still against gusting wind. Airplanes use it for autopilot, for fly-by-wire, for flight stability augmentation. Your car uses it for cruise control, anti-lock brakes, electronic stability control, and soon for self-driving. Your thermostat, your pacemaker, ventilators in hospitals, the power grid balancing supply and demand across an entire continent 60 times a second. Factory robot arms, chemical plants, oil refineries, hard drive red heads tracking nanometers, camera gimbals stabilizing video on a moving skateboard, rocket engine throttles, even the inverter in your microwave oven. Right now, as you watch this video, there are literally billions of feedback loops running across the planet. Same mathematical toolkit, just tuned for different jobs, working silently, reliably, invisibly. Control theory is engineering's invisible infrastructure. 2 centuries of mathematics, starting with James Watt's flyball governor keeping steam engines from blowing up in the 1780s, all the way to a SpaceX booster landing itself on a floating drone ship in the middle of the Atlantic Ocean in 2024, distilled into a set of tools that every modern engineer uses. It's what lets machines behave intelligently in a world that is constantly, relentlessly pushing back. Wind, gravity, noise, unpredictable inputs. The next time you watch a rocket land or a drone hover or your thermostat hold temperature while the outside weather shifts wildly, look a little closer. You'll find a feedback loop, probably a PID controller, maybe an LQR, maybe a Kalman filter, maybe a full MPC stack. Elegantly applied, silently, reliably, working. That's control theory. 200 years of math, keeping the world behaved. If this blew your mind, hit like and subscribe. New engineering deep dives every week.